This is Jack Jackson. Today we're going to be looking at bivariate data and talk about the ideas of a line of best fit, regression, finding that line, how do we measure it, and then correlation, which is going to be a measure of how well that line fits the data. So let's start with talking about what we mean by bivariate data. So bivariate data, we have both input and output pairs, and generally what we're going to be looking at here is real valued interval or ratio data. And we can, for example, we can use our TI-84 or similar calculator to compute some basic descriptive statistics. So let's look at a quick little simple example here with 4 data points. We have pairs of data, ordered pairs. We have pairs of data, ordered pairs here, where we have the input and output pairs. The input is time and the output is temperature. We can go to our TI-84, go to Stat, Edit, choose, first of all, go to Stat, Edit, go to our screen here, go to List 1, put our cursor on List 1, clear that out, hit Clear and Enter, type in that data, just like we've done before for one variable statistics. In List 2, type in your Y values, so your X values are in List 1, your Y values are List 2. Then calculate 2 variable statistics by going to Stat, Calc, and you will see 2 variable statistics, then give it, Stat Calc will give you this screen here, choose number 2, then type in L1, comma L2. L1, remember, is second 1, and L2 is second 2. And then hit Enter, and you'll get these screens down here. You'll get this first screen. There's an arrow, so you go down, and you'll have to go down quite a bit to get all of the information here. But notice it will give you the sum of the x's, the number of data points, n is 4. It will give you the sum of the x squares, that is, square all the data and add them up. Okay, and it will give you x bar, and then it'll give you the sample standard deviation of the x's. And if this was a full population, then we'd use this sigma for the x's for the standard deviation. You go down, and it similarly gives you the same information for y's, the y bar, the sum of the y's, the sum of the y squares, and the standard deviation of the y. It also gives you the sum of the product of the x and y. So, in other words, take the 10 times 100, the 20 times the 110, the 30 times the 124, and the 40 times 129, and add those 4 products up, and that gives you this number here. Let's see here. If you go down, it gives you the minimum and maximum x and y values. So, pretty straightforward for some basic descriptive statistics. Now, we can also think of these, since the ordered pairs are of real numbers, we can think of these input-output pairs as being points in a Cartesian coordinate system, our regular graphing rectangular coordinate system. And we can graph the dots on a piece of graph paper, and we can get the calculator to give us the same graph. And this type of graph is called a scatter plot. So the way to do that on your calculator is you go to Stat Plot, turn your plots on, go to number 1, choose that, turn it on. Notice we're choosing this one right here, the first one here, that's the dots. Our x's need to come from list 1, our y's from list 2. We have 3 choices for the mark. I like the first one. And we get these little boxes for the points. Now, we need to get this to graph. Before you do this, you probably want to go to your y equals screen and turn off all your graphs first, all your other graphs. So this is the only thing showing. Now we need to set an appropriate window. We could do that by hand, but we can also do that by doing zoom 9, which is zoom stat, and it will automatically pick a window for us, which you see here, and that gives us a graph. So that's a scatter plot. We can do a similar thing in Graphmatica. It gives us a scatter plot here, or in Excel, and we can get some dots here. Now, what does it mean to find a line that might approximate that data? So I'm going to look at a Geometer Sketchpad sketch with another set of data. This one has 6 data points. Now this is a dynamic sketch so that these data values can be changed, but once we fix these, that's going to be set for the duration of our demonstration here. So I have a data set with 6 data points here. And it is, let's actually change this a little bit. Let's say maybe that's a 2, maybe that's a 5, maybe this is a 13, and maybe that's a -3, let's say. Okay, so we have some data values. And notice it adds up the y's and it adds up the x's here. Okay, now suppose we want to get a graph of that. We need a coordinate system here, which we have, and we can plot the dots on this coordinate system. And so we see some dots here. Now we notice that these particular dots are not in a straight line, but they're close to a straight line. So we can take a line here and see how well this line fits. Now this particular line is controlled by these points D and C. Now we could, for example, make it go through, say, the first 2 points, but then it's likely to miss the other points. Or we could go to the first and last one, and it may miss the others. Okay, so there are different places we could put this line. So let's say we wanted to make this line here approximate the data. It's not a particularly good fitting line, but let's say that's the line we're going to use for the moment. Okay, how can we measure how well that line fits? Well, the first thing to notice is that if we keep those same x's, we have predicted points along that line. Those are these green points right here as we're going down the line. They have the same x values as these original ones, but the y values here. So in other words, let's go back. This point here, P1, has coordinates x1, y1, which is 1, 13. Point P2 is 2, 11, as you can see. The predicted point with the same x value as P1 is this point right here. That is x1, y, P1, y predicted 1. So that has the point 1, 6.07. And likewise, the predicted point with the same x2 is 2, 5.37, which you can see the coordinates there. And so now we can compute those using the equation of the line that we have. We can predict these y values, the same x values that we have in our data. Now notice that these miss some or all of the actual points. So we can find how far they miss by what are called the errors. Okay, the errors are which is the y minus the y actual minus the y predicted. So we take the 13 minus the 6.07 to get an error of the first one that is 6.93. So the actual value is above the predicted value by 6.93. This last one has an error that's below. Now we could add up these errors, some of the errors, but that itself is not that particularly useful to us. Because think about it, you could have some really large positive errors and some really large negative errors, and they would cancel out. Now what we could do is take the absolute value of those errors and add them up. That would be the sum of the absolute errors, but that's typically not what we use. In the same way that we use the squares of the deviations from the mean to compute the standard deviation and the variance, we're going to use squares of these errors here. So what we're doing is we're taking these errors and squaring them. Notice geometrically what that does is take these lengths, so the lengths of these purple lines here are the absolute values of these errors. But if we square them, we get the areas of these squares. Okay, so there's one, there's another one, and so there are 6 of these squares, and we add up those errors, and that's what we have right here, the sum of the square errors, SSE. And so that's our measure of how good a fit this is. So what we want to do is take this and manipulate the line. Now, can we get a smaller SSE? So this is a really, really bad line here, huge SSE. Okay, this is better. We could take one that goes through the first 2 points. What does that give us? Something around 70 for SSE. Okay, what about this? Well, that's a little better, 62. Can we adjust it and make it better? What do we need to do? We can move these 2 points. Let's see, maybe move this one down. Oh, now it's getting better. Better, okay. 13, 12, something. Oops, worse. Maybe I could move this one up a little bit. What's my best thing I can come up with? So each one of these, so there's a smaller SSE, it's coming closer to hitting those data points, and it's a better fitting line. I had one at 13 point something a minute ago. Let's see if I can get back to that. Oh, there's 12.68. That's pretty good. I don't know if that's the absolute best possible one, but that is one that fits pretty well. So now the question is, what do we do? What do we mean by the best fitting line? Okay. Well, with a given data set, we can compute this SSE for any particular line that we have. So the one of those lines that is the smallest SSE of all possible lines, each one produces an SSE. Which one of those is the smallest SSE? Then the line that corresponds to that one is our best fitting line. And that's where we make our sum of the square errors the least possible. So that's called a least squares regression line. And that's the one we're going to interpret as being the best fitting line. So this goes through the steps. So we compute a set of data, we produce a scatter plot. We can approximate the plot with any line we want. Given a line, we can compute the predicted y values on the line at the given x values. Compute the errors by subtracting these predicted y values from the corresponding actual y values from the data set. Square these errors. Sum the square errors. This is the sum of the square errors, SSE, which is a measure of the fit of the line. For a particular data set, a line with the smaller SSE is considered a better fitting model. The line with the least SSE is the least squares regression line. And here is a now slightly different data set than the one I worked with there. Here's a rather poor approximation, and then the next slide is a better approximation. In fact, this one's very close to the best approximation. Now, how do we find that least squares regression line? Okay, let's see. Let's hide this, and let's hide some stuff here. So now we're back to our data set. It turns out that the least squares regression line goes through the centroid. Okay, now the centroid is the coordinates has the coordinates x bar and y bar. So x bar is just the mean of the x's. So we add up all the x's and divide by how many we have. Now in this particular sketch, the data set always has to have 6 points. We can change the numbers here, but it has to have 6 points. And of course, in a reality, you can do this with any size data set. So we have our x's here, add them up, divide by the number, and that gives us a mean, x bar. Similarly, we can find y bar, and that the coordinates there, x and x bar, y bar, are the coordinates of this point right over here called the centroid. And I've got vertical and horizontal lines drawn there from the centroid. And so this is y bar is that all the points on that line, and x bar is all the points on that line, and x bar y bar is the single point, the centroid. Okay, so to compute the regression line, here's what we do. Well, before I do this, let me explain something very briefly. Coming up with this process is actually what we call an optimization problem. It turns out that that's exactly one of the reasons why calculus was invented, and one of the real strengths of calculus is it's solving optimization problems. So it turns out that it's actually a Calculus 3 project to figure out the appropriate technique and formula for doing this. Now, the good news for us is right now we don't have to know the calculus or know any calculus at all to be able to do this. What we need to do is do the process. So the process that comes out of that calculus project is actually an algebra or arithmetic kind of process, and that's what we're going to be looking at here today. So here's how we compute this algebraic process. Okay, a lot of data just came up here. Let's look at it a bit at a time here. Move this. There we go. We can't see 0.6, but we'll get back to that in a minute if we need it. Okay. So what we want to do here is, first of all, figure out from each x value, figure out how far it is from x bar. That is, figure the distance horizontally to this vertical line. Okay? And we take all of those, and that figures out xk minus x bar. So in other words, we know x bar is 6.17, so we take 1 minus 6.17, that's negative 5.17. And then we do 2 minus 6.17, that's negative 4.17. So this point here, 1, is 5.17 units to the left of this vertical line at x equals x bar. This one, point 2, is 4.17 units to the left. And how do we find point 3? Well, point 3, we find that actually by doing 4 minus 6.17, which is negative 2.17, so it's 2.17 to the left of here. These points turn out to be the right of the x bar, right of this vertical line, and this is how much they are to the right. So those are the x sub k's minus x bars. Similarly, we can find the yk minus y bar. So we take the y value here and find its distance from this horizontal line, and that is this value here, say for this first one. So take the distance from there down to here. That's going to give you this y value here, that difference here. So that, how do we compute that? Well, that's the y value of this point, which is the 13, minus the y value of the horizontal line, or the centroid, which is the y bar. So 13 minus 5 is 8. So that's a distance of 8 from here down to here. And so we do all of these vertical distances from the average, and we get those. Horizontal distances from the average x are in the maroon here, and the purple numbers are the vertical distances from the average y. Now we're going to compute some products here. We're going to take all of these purple, these maroon ones here, the xk's minus x bars, and we're going to square them to get these blue numbers here. Similarly, we can square all the differences from the y's to get these 10 numbers over here. And we can multiply these here to get these black numbers here in the middle. So, for example, negative 5.17 times 8 is the negative 41.33. This one here, negative 4.17 times 6 is the negative 25. Or we can take negative 4.17 and square it to get 16.37. 6.83 squared is 46.69. Negative 8 squared is 64. Negative 4 squared is 16, and so forth. And then we add up these three columns. So we add up the xk's minus x bar squares. We're calling that S of xx. S sub xx. That's the sum of the squares of the deviations of our individual points from the average x. In this case, that's 110.83 when you add up all these blue numbers right here. Add these numbers up, and you get this number down here. Similarly, we can add up the xy's, these products here, and adding up these numbers here, we're adding up all the xk minus x bars times the yk minus y bars. That gives us this number down here, negative 138. And we also then can similarly do the add up the tan numbers here. That's s sub yy. It's also sometimes called SST, sum of the squares total. Now we use those numbers then to compute the, or at least some of those numbers, we use them to compute the equation of the regression line. Okay, first of all, when we find a line, remember the formula for a line is y equals mx plus y sub 0. The m is the slope of the line, and the slope of the line is found by taking the sxy, that's the negative 138 in this case, divided by the sxx, the 110.83. So you take that number divided by that number. In this case, it rounds off to negative 1.25. That's the slope of our line. And since we know it goes through the centroid, we know this from the calculus project that we haven't done here, so we're gonna trust that project. And if it does go through the centroid and it has this slope, you know that well, anytime you know to find the y-intercept, you take a y-coordinate you know minus m times the x-coordinate you know that's on the line. And we know it goes through x bar, y bar, so we know the y-intercept, y sub 0, y-coordinate of the y-intercept, is y bar minus m times x bar, and we can use that formula to do that. So that means that the regression line is y equals mx plus y sub 0, or in our case, y equals negative 1.25x plus 12.68, and that is the best fitting line right there. That will have the smallest SSE. Okay, so let me hide a couple of things here. So let's hide that computation, but keep the line there. Let's go back to show our variable line, and if I can get that line to match the line here, it's going to be difficult to get it to match perfectly, but maybe I can get it to match at least approximately. Being close. That's really close right there. Okay, and we can see the square errors on that line, 12.17, and notice that was quite a bit smaller than what we had seen on some of the other lines that we had looked at as possibilities earlier. So if we go back to our PowerPoint slide, let's review what we do here to find the least squares regression line. Given a set of data, we compute the mean of the x values and the mean of the y values. That's x bar and y bar. Those are the coordinates of the centroid, which will be on the least squares regression line. We find the difference of the x values from the data, from the x bar, and one of those for each data value. And then we do the same thing for the y's, take the y values minus the y bar for every y value. Then we can compute these following sums, SXX, SXY, and SYY. Actually, we don't need SYY for the computation. We only need SXX and SXY. SYY will be used a little bit later on for something else. but we'll use these two things here. We find the slope, which I'm going to use the standard letter M. Sometimes in statistics they'll call that b sub 1. That is s sub xy over s sub xx. And then the y sub 0, or b sub 0, is y bar minus m times x bar. And then your equation of your line is y equals mx plus y sub 0. And for our other data set that we had over here earlier in this slideshow, here is the set of computations for it. Okay, so you can look that over. Now, so of all the possible lines that we could pick, we can use this technique to find the single line that is the best fitting line. This is the least squares regression line. But then the question comes, how well does that line fit? Well, one way we could measure the fit of that line is do the SSE of that particular line. But the problem with that, if we're going to compare that to a different data set, the data sets could have different numbers of points. And so we could say we have the line fitting one set of data versus a line fitting a different set of data. If they had the same number of points, we could compare SSE from one to the next. But if they don't have the same number of data points, we need to somehow take into account the number of data points a little bit and work that out so that we'd like to have a way of comparing the fit from one data set to another data set of the line, of the regression line. We know the regression line is the best fitting line that we can come up with, but still, that could be a good fit or not a good fit. In fact, it might be perfect. All your data might be actually in a straight line, then you'd have a perfect fitting line. Or it could be that your data doesn't look at all like a line. How do we measure that? Well, then that's what we're going to do is called correlation or coefficient of determination are going to be ways of measuring that. So let's take a look at that now on our sketch. So we have the line of best fit now to this particular data set. It's plotted in our blue line there, and we have the formula for it. But how do we measure how good it is? Well, we can measure how far off we are. These are sometimes called the residuals or errors. And so let's look at our computation. Now, this computation here. Okay, and so let's look at this. So just like we did with any line, we can compute the errors. To do that, we need to first get the predicted values. So we want to find the values on this line, these guys right here, with the same x's but different y's. Y's from the equation down here. So we take this equation, plug in these x's to find the y's. In other words, if you put a 1 in this equation here, negative 1.25 times 1 plus 12.68, you get 11.43. And you do that for each one. So you plug, and that gives you, by the way, this coordinates, y coordinates at that point right there with the same x as P1, but the y coming from the line, not from the data set. Similarly, you do the same thing. Take the point P2, take its x, figure out the y value that's on the line there, not the y value that was actually given. So we ignore the 11, take the 2, put it in this formula down here, and you get an output of 10.19, which is the y value right here. Do that for all of these, and you get all of these numbers here, which are your errors, or sometimes also called residuals. I'm sorry, not yet. Those are just the predicted values. So those are y predicted. Take the y actual minus the y predicted, so 13 minus 11.43, that gives you your error or your residual, which is the purple. So the purple is the error or the residual, which over here is actually these vertical links in red. Square them, we get the square errors. I haven't drawn those out as squares, but as we saw before, that will give us our square errors. As we saw before, these should be basically the same thing that we did before, these values right here, to compute those square errors. Now, we sum those up. That's our SSE, which is 12.17. And again, no matter which line we pick, it's going to have a larger SSE than that, except for this line right here. This is the one with the smallest SSE. Now we can also compute some things here. We can take the y predicted minus y bar. So take the 13 minus the 5. I'm sorry, no. The y predicted. The 11.43 minus the y bar. There we go. Take that difference, and that is, well, this ER1 is what I've called it. And that is a difference from a y predicted, subtract the y bar. That gives us this value here. So that's a distance here, a y distance from this point here straight down to this line here. So that distance there is the 6.43. Some of them are below, if it's below the y bar line, then those distances will be will have negatives in front of them for these. Square those amounts, so take the 6.43 and square it to get the 41.38. Repeat this for all of the different y's. So we're taking, again, the y predicted minus the y bar to get these guys here. Then take these errors here and these values, these deviations from y bar, from the predicted y's from the y bars, and square them. And sum those up. Those are the sum of the squares from the regression, differences from the regression line from the average. Okay, that's SSR. Now, it turns out that if you take SSE plus SSR, you get SST, which is the same as S sub YY that we looked at earlier. So S sub YY we computed earlier, and that is SSE plus SSR. Okay? Now, we can use these to come up with two measures that are related here for how well this line fits. The first one's called the coefficient of determination right here, called R square, lowercase r square. And that's SSR divided by SST. So that's 1.71 or 171.68 divided by the 183.85. SSR divided by SST, and that gives us 0.93. Now this is a ratio of of the total deviations, total squares of the deviations of the actual values from here. So remember that this one here, the S of YY's, we're taking the Y's here, taking their differences from the Y bar, squaring all those and adding them up. SSR is taking the Y values along the line here, the predicted Y's, taking their differences from Y bar, squaring those and adding them up. And we're doing a ratio of those. So notice that what's going to happen is that you always get something here, it turns out, between 0 and 1. And so we can think of this in percentage form, and what we can think of here is the R square is the percentage of the deviation from the average line down here, from the average Y. What percentage of that is accounted for by the regression equation? So this is saying that 93% of the variations in the data, in the Y values of the data, actually come from this explanation that is given by this relationship of the regression line. Now, it turns out there's an alternative formula for this, but if we take the coefficient of determination, the R square, we take its square root and then give it the same sign as the slope of this regression line. That's what this SGN of m means. Take the slope of the regression line m, take its sign, which is either positive 1 or negative 1. So positive, negative, times that square root of r squared, and which is, this case is a negative slope, so it's a negative 0.97 when you take the square root of that, but you want the negative square root because it's a negative slope to the line. That's called the correlation coefficient, or just the correlation, or sometimes named after the statistician Pearson, the Pearson correlation coefficient. And so that turns out to be also a measure of the line. So notice that that r squared will be 1 if it's a perfectly fitting line, and r squared close to 0 is a very bad line. R squared close to 1 is a very good fitting line. Similarly, if the absolute value of r is close to 1, it's close to a very, very good fit. If r equals 1 or negative 1, it's a perfect fit. If the r is positive, then we have an increasing relationship between the two variables. So increasing one variable increases the other. In other words, your regression line has a positive slope. And an r with a negative r, like we have here, says that increasing x is going to decrease y. And so we have a negative slope to our regression line. So these are the predicted outputs, you can see, and the gray lines there are the deviations of the predicted values from the y-bar. So those gray links are, well, with positive or negative on them, are these values right here. Okay. Alright, moving back to our PowerPoint slide. So here are the basic formulas. Take a set of data. First of all, we compute the least squares regression line, as we did in the previous slides. We compute the coefficient determination r squared and the correlation r with the following formulas. Remember SSE, which we don't really need for this, but that was one measure of the fit of the line. We took our predicted y's minus our actual y's. We do this, the k just counts up each, the first one, the second one, the third one. For each point that we have, square those differences and add them up. That's the SSE, sum of the square errors. The sum of the square for the residuals, sum of the square for the regression equation, SSR, is we take the y predicted, which is from the regression equation, take each one of those, find its deviation from the y-bar, that was the gray links that we saw just a minute ago, or the numbers in black on our previous screen, square those and add them up. That's SSR. SST is S sub YY that we looked at earlier. You take the y actual minus the y bars, square those differences and add them up. To get r squared, the coefficient of determination, it's SSR over SST. And one way to compute the r value is to just take the square root of r squared, but give it the same sign as the slope. Here is the computation for the data that we were looking at earlier in the slideshow, so that if you print out these slides, you will have an example worked out. And again, here's the interpretation that we've already gone over. The coefficient determination, r squared, is always a value from 0 to 1. R squared equals 1 indicates a perfect fit to the data. Your data really is in a line. R squared close to 1 indicates a good fit. R squared close to 0 is a very bad fit. R squared, if you put it in percent form, is the percentage of the variation in the data from y bar that is described or accounted for by the regression equation. We can get a similar interpretation just by looking at the correlation R. R, that should be a lowercase r, is between negative 1 and 1 inclusive. R has the same sign as the slope of the regression equation, so a positive r indicates an increasing relationship between the two variables. Negative r indicates a decreasing relationship between the two variables and a negative slope to your regression equation. Absolute value of r equals 1 is a perfect linear fit, and absolute value r close to 1 is a good fit. Close to 0 for absolute value of r is a bad fit. One final warning. A strong correlation does not necessarily indicate that changing one variable causes a linear change in the other variable. There may be hidden, lurking variables. Here's a good example of this. Reading level in elementary school is positively correlated with shoe size. So, the larger the shoe size, the higher the reading level. The higher the reading level, the larger the shoe size, as a general trend. However, increasing the shoe size does not cause a higher reading level, nor does a higher reading level cause a larger shoe size. There are lurking variables here are the age of the students and the amount of school and training and education the students have received. So increasing these variables, the age of the student and the amount of reading that they've done and teaching that they've had about reading, these are likely to increase their reading level, and also increasing the age is going to likely increase the shoe size for these elementary school students. So there's not really a cause and effect relationship between shoe size and reading level, even though they are positively correlated. So be careful to not assume that the correlation implies causation. I saw a comic strip once that had the two statistics students talking about their statistics class, and the one student said, "Wow, we had a really good statistics class this year, and we talked about causation and correlation and all kinds of good linear regression in our class." And the other student said, "Wow, you must have really learned a lot in this." And he says, "Well, maybe and maybe not." So we have there some information about descriptive statistics in terms of linear regression. We've talked about what we mean by measuring a line of best fit. We've seen that geometrically and numerically and algebraically. We've also talked about how we compute a line of best fit, a least squares regression line. Again, we've seen how to interpret that geometrically and algebraically and numerically. We've talked about measuring a line of best fit through correlation and coefficient determination, and again, how to compute that and how to visualize that geometrically. Now, it turns out that these things are actually built into several different technological means, such as our calculators, Excel, and some other programs as well. So in a later video, we'll talk about how we can use technology to compute these things.